The first thing I want to say is if you look up on the screen, you'll see that our panel moderator is listed as Ed Morris, but I got an email from Ed on Monday night, and some guy named Barack Obama got his attention, and apparently he got called to the White House today. So he arranged for a substitute who is Jim Williams, and I really appreciate Jim doing this at truly the 11th hour. And Jim's in the group getting his photo taken right now, but Jim's the Vice President of Aerospace and Defense and Advanced Manufacturing or Additive Manufacturing R&D, and he's also involved pretty heavily with program and business development for the 3D Systems Corporation in Pennsylvania. So really appreciate Jim substituting at the last minute on this panel. I think if you've been to the plenary sessions, I think every plenary speaker has mentioned worked in additive manufacturing into their talk. And so I know there's a lot of interest in it in the industry and in this conference in particular. My name is Tom Irvin. I'm chairing something called the integration tier this year at SciTech. Although you may not have seen that name before, the integration tier is an attempt by AIAA to sort of expand what we offer to people in the industry and to aerospace professionals and try to broaden the reach or interest in AIAA and what AIAA has to offer beyond the more typical R&D community. So like all of you, I am really looking forward to this panel this morning, and with that I'm going to turn it over to Jim.
Thank you very much. Sure. Gentlemen, you want to come up and have a seat?
Yeah, where do we sit is the next question.
Sorry. Grab the third chair.
This is me?
Third chair.
Okay.
Next one.
First, I'd like to say it's my pleasure to be standing in for Ed Morris. I've had the opportunity on several occasions to be present when Ed's done a presentation, and I hope I could do him justice. My name is Jim Williams. As you learned, I'm with 3D Systems. 3D Systems has been the probably the longest in the race in this industry. Actually, first invention came out of 3D Systems in 1983. Patents were filed in 1986. So we actually celebrated 30 years last year, or I should say Chuck Hall did, who was still with the company as CTO. My company, prior to becoming part of 3D Systems in 2012, was a small business up in Pennsylvania, Paramount Industries. And some of the things that we accomplished were directly related to where we're at today in terms of the industry, some of the things that we were trying to pull forward and push, more to do with materials and advanced materials for polymers materials for selective laser sintering. So my company was a product development company. We happened to pick up additive manufacturing in the early 90s. At the time it was pretty much used as communication tools for visual prototypes. And along the way, we started doing work as the industry did, trying to advance it and push it further into tooling to the point where we are today. We're actually putting parts on aircraft and systems that are beyond just aircraft. So what we're going to hear today from the panelists is their experiences, how they're applying the technology, what level they see the applications for the future, where they're at today. I think you'll see some great examples. What I certainly hope that we can encourage is a lot of audience participation. There is a lot that we still need to do in this industry to make it a robust manufacturing process. We're working hard, but we need to hear a lot of voices. I think more importantly is what we need to hear is a lot of people becoming interested in it to see how it would fit into their business, what kind of strategies they need to have in order to have it flow down through the ranks and become pervasive within your organization. That is the goal of, certainly the goal of Additive, certainly the community. It's certainly the goal of America Makes. Since I'm representing America Makes today, I'll spend a little time speaking to that. With us today, I have Bill Flight from Lockheed Martin, and I'll go through their bios at the end of my presentation as I do their formal introductions. Dan Johns from Chief Technologies for GKN, Eric McDonald from UTEP, University of Texas, El Paso, and Paul Cisello from Ford. So with that, next slide, please. Oh, I got it here. Okay, here we go. So, you know, it's hard to avoid the media with additive manufacturing in 2013. Now, for someone who watches the stock, I hope 2014 is as good as 2013 was. But frankly, there's been an awful lot of really success stories brought forward into the media, which after my time in this industry, which is basically started in the late 80s, it's amazing what a couple of years can do with some voices from Washington and investment coming out of the government. And I think we'll learn a little bit about that today. So what you have in front of you is basically some highlights, some of the news media clips. The first part to your left, upper left, is a glove that was done by Oak Ridge National Laboratories. It's all metal, it's printed. That glove actually operates, it's not a glove, actually it's a prosthetic. And it actually is made out of titanium, and it works on hydraulics, and it's 3,000 PSI. So it was a substantial accomplishment for what Oak Ridge pulled off there. The next gentleman behind Wired is Bray Pettis. Bray was the gentleman who broke the mold on IP. Basically, when the Stratasys, which is one of our technologies that we use in the industry, not certainly 3D Systems, but a competitor, if you will, basically went ahead and took advantage of the IP when it became a public IP. And with that, basically began a revolution. There was others that preceded him, but he certainly has one that's gotten a lot of notoriety as a result of that. And then who could ignore the economist with Print Me a Stradivarius? That particular material is a material that is very close to me because it's something that I processed as a small business prior to joining 3D, and I still do to this day, and I can speak a little bit to that. But the next machine, Modern Machine Shop, was a partner that I worked with on one of a small business innovation research grant from Air Force, and what we were assigned to do, we had a $4 million critical SBIR to put polymer parts, high temperature polymer parts that were ESD compliant on the F-35. I am very proud to say that I expect to insert the first parts. That partner's dropped away, but I kind of stayed for the long haul, and I'm committed to make sure that we get parts on the F-35 that are printed in high temperature polymer and that are carbon filled. I can't see, well, I can look down here. I think one of the stuff that gets the media's attention are the things like the guitars and the jewelry and the real consumer, but that's what really gets the attention, because we've been pushing manufacturing for some time, but we haven't gotten the attention. But now, because of that, and it's not the answer, it's not the only reason why, but I think because of that, we're seeing a lot of interest at the top end of corporations, the CEOs, and they're saying, where's our strategy at? What do we need to be doing? And how do we make this pervasive, or should we make this pervasive within our company? So I think that you'll get from the panelists today varying views of that. And I trust that they'll probably be mixed depending upon who they are and what industry they're in. And in medical, there's a plethora of applications that have been touched today. And I think what's really unique about additive manufacturing is there really is no holds barred. There is not one manufacturing process, or I should say industry, that can't benefit from additive manufacturing. Even clothing, it's hard to believe, but even clothing. at some point we're going to see additive manufacturing adding some value to that industry. I don't know exactly what. We're seeing it beginning in food now. 3D Systems just recently acquired a company that prints food, so we're going to see more of that, I'm sure. But you know, there's plenty of opportunities to explore the unknown, and that's what really additive gives you, and you'll see why, I think, as we go on. So, you know, as we talk about, you know, what really is the driving forces that, why is it so important? What's the benefit? What Ed's put together here is a few, kind of a snapshot. Some that really resonate with me is, you know, complexity. You know, the ability to design things that you couldn't manufacture or wouldn't manufacture otherwise because of the expense. I think that is really the holy grail that I think will really drive this industry, allows us to invent without the constraints of traditional manufacturing thinking. And that's where the education comes in and the design tools that we need to have to drive the industry. Lightweight structures, which is something that's very close to my heart, where we developed a conformal lattice structure as a small business, and we're finally now getting the traction within 3D Systems to get it into a commercial. There's other companies that have done similar things. The idea behind it is really, you know, we don't need all the material. What we really need is improved performance, lighter weight, longer distance, fuel, all those kinds of things. And these kinds of developments, design tools, or design approaches are exactly what we need in order to make this technology more pervasive, because the only way you can manufacture the part is with additive if you use these kinds of technologies, design tools. Cost reduction, tooling reduction, you eliminate complete tooling phases, so weeks, sometimes months are converted into days, and I think that's always been there. You know, in the beginning of this technology, what we looked at was business practices. I think the biggest impact in the 90s, early 90s and coming through the 90s, was how can we change business practices so that we reduce the time to market. The big issue was time to market, and a lot of consumer companies were pushing it because they could reduce their cycle just because of, and then that grew into aerospace where they looked at it as visualization tools, and then they started adopting it into actual platforms. And one of the best opportunities the industry had for adoption was in some of the UAVs that came about as a result of the you know, what we've been going through in the last 10, 13 years, I should say. So, and that's driven additive manufacturing to aerospace because of those needs coming out of our warfighters' requirements and what they need to have to be the best that they can be. Small lot production, one-offs are what someone would call prototypes, and others would call it my game. You know, if we do something for NASA, they only do one. They might do 10 to get to one, but they only do one. So it all depends on your paradigm, whether you see it as a production or you see it as a prototype and or a visualization tool. But however you manifest to use this technology, it's going to add value to your customer, to yourselves, to your process. Agility. You know, localized manufacturing is a big buzz today. Being able to put a machine on the moon or wherever we might go to. We're going to be doing printing in space very shortly here. NASA has a program. I guess it's pretty close to being launched, if I'm not mistaken. I know 3D Systems has played a part in that, but other companies are also playing a part in that. So there's really interesting things developing around the whole idea of localized manufacturing and supply chain management. And I think that you know, a great example of that is being able to use it in theater and for our warfighters, being able to stand up a Connex with a machine inside where they can make a part that who knows what they're using it for. It could be to hide something, or it could be to actually demonstrate something that would benefit the warfighter, where they can send it back to the U.S. and have it develop further, or perhaps just use it. So there's a lot of interesting ideas behind what you could do with this in many different ways. Next slide. So these are but a few examples of localized manufacturing, localized production. The slide, the photograph to the far right was, I don't know a whole lot about this, but I do know that this gentleman set up and was actually using sand as the material. So he was running the machine solar in the desert. So the whole thing was just kind of like a system made just, take the materials from where you're standing and use them in your machine and make a part. Perhaps, Eric, you might know a little bit more about that. I don't know a whole lot of detail. UAVs, launching them, but printing the UAV as the manufacturing process. I did it. I mean, I flew a plane. There's others that have as well. Where we're, and the cost reduction and the time reduction is crazy. I mean, I can print in one machine, I can print 30 aircraft and then within days send them to the customer so they can get them up and flying. That's the kind of stuff that, and it's, so DoD has a huge benefit, opportunity to benefit from this in ways, but I believe others do as well. Again, high value, complex parts. One of the things that has, a lot of companies have explored is taking multiple parts and making it into one part. I've had the opportunity to look at complex systems that were developed 50, 60 years ago and recommend how they could put these parts together and make one piece instead of having to have 10, 15, 20 pieces. It reduces the pile of paper. So your supply chain is immensely impacted in a positive way, which is a cost savings. Time to get it into the system from order to being on the shelf is immensely reduced. So legacy parts, it opens up a big opportunity for spares that ground a lot of very expensive assets for a long period of time because the depots can't keep pace with it. And they have to go back to the original way. There's a lot of challenges to make that happen. I mean, it's not trivial what we have to accomplish in the next months and years, but we're going to do it. And of course, the medical world. I mean, it's amazing what impact this technology can have on the medical side. I've witnessed. I've actually made parts for companies that are adopting knee surgeries where they're scanning the person. So you get this actual copy of the person that when they scan it and CT scan it, and they take that and with their software create the actual implant, which is typically titanium. That can be machined. It can be investment cast, but today it's actually being printed in titanium and follow-on machining. The parts that they use to drill guides and assemble it to the actual bones is all printed. So you go into surgery in 6 weeks from the time you get a scan and you get a knee replacement with your knee, literally scanned out of your body. So I mean, it's amazing. And we're talking about 400,000 knee implants this year. It's like in 5 years, it's going to be 4 million a year because of all those of us who grew up as, we can now go and buy a knee, and if we feel bad, we can just, go get a knee. And I think a lot of people will be getting these. And they'll be printed. America Makes, near and dear to me. I am on the executive committee. 3D Systems is a solid supporter, as many companies are, Lockheed, and I trust that GKN is and UTEP is. So the idea behind America Makes is really it's a National Additive Manufacturing Institute. And what the core, and I'm sure Ed would have a different take on this, but from my perspective, it's really to make this technology pervasive. It's to give a place that you can go to get information and get projects done. Research projects, but not raw research, but where you're looking at getting something, taking it from like a MRL3, if you're sitting there, and moving it towards production. It's a place to mature something. They have a lot of talent, but the biggest talent they have is their ability to get a collaborative community together. It's a private-public partnership. There was initially a $30 million award that came out of a competed process from the government. Up here you'll see the badges of the various agencies that support the initial $30 million. It looks like it has another $15 million that's pledged from the government to continue. It has basically was given 3 years and $30 million. And you know, I can certainly give you a lot more detail on the purpose about the projects and how they're spending the $30 million. But I believe they just announced yesterday the awards for $9 million of that $30 million that went out to the community. It went back to the members, those who put proposals together, and those proposals came out of a very rigorous, very state-of-the-art approach to creating a roadmap, and a roadmap that was created by the community, across the country. It wasn't limited to just a regional area or a few people that showed up at a conference. It was a very, very tedious approach, but a very effective approach to collect a lot of information. I think there were probably close to 1,500 data points that came into this, and it was sorted out by the leadership of America Makes to come out with proposals. And I believe they had received over 100 intents to bid, and it boiled down to about 45 at the end who actually put proposals in, and they made 15 awards. I think yesterday they announced them. So that's America Makes. They're, to say they're located in Youngstown, Ohio, is only a physical presence. They're really located across the United States. You know, our mission is really to be everywhere where there needs to be a knowledge base or an education or workforce to kind of make this technology pervasive and across our nation. And it's about jobs. It's about looking at advanced technologies like additive to create a future for our country. So I mentioned briefly that the mission of America Makes falls into a sweet spot of MRL, manufacturing readiness level, or technology readiness level 4 through 7. So we're not taking away from the universities. We're not doing that kind of heavy lifting to create and invent the core technology, the material or the process, but really enabling them with more funding and with a lot of interesting collaboration, interesting community of collaborators that at their beck and call to participate, to move it through and into the gate, you know, just to the gate of ready for production, which is an MRL 7. The next step would be MRL 8, which would be pulled through usually with more money and a different group of people perhaps. So with that, watching my time here, which I need to, what I'd like to do is introduce each of our panelists, and I would like to begin with Bill. And Bill is, oh, I'm on the wrong side, Bill, sorry. It's the moment. So Bill is senior manager, he's Lockheed Martin, and we had a chance to talk, and he actually knows some people, I know some of the people that he works with, so we have a lot of things to chat about, but he's advanced manufacturing and corporate engineering technology. Bill works across the enterprise to develop and maintain the engineering skill set and tools necessary to effectively design and manufacture Lockheed's portfolio of products. His focus is on accelerating manufacturing, innovation in key technologies areas. Bill is founder and co-chair of Lockheed Martin's direct digital manufacturing community of practice and former chair of the Manufacturing Fellows Action Team. He was also part of the NNMIs. You may have been aware of the National Network for Manufacturing Innovation that was announced by the administration last year. Time flies, perhaps 2011? 2012, excuse me. So out of that, there were supposed to be 15 national institutes of advanced manufacturing, the first of which was America Makes as a pilot institute, and then 3 others were recently announced. So I think that's the NMI that Bill is referring to. He's been principally involved or heavily involved with workforce development and education within Lockheed Martin, and he can certainly speak to that. And he is the representative of AIAA Engineering Management Committee, a member of NDIA, and a member of the NDIA Manufacturing Division. So the next individual is Don Johns, Chief Technologist for GKN Aerospace. Dan is, and I'm reading through his bio today, he also told me he used to work for 3D Systems. We didn't explore that very much, but so let me ask you, did you drive that car 1,000 miles an hour? Is that something that you actually did?
No, it's still being produced.
It's still being produced, okay. So he's got a very interesting job, actually, so he can talk a little bit about that perhaps. So he was first introduced in the early 90s to this technology. Some of his areas of accomplishment was the Trent 900 flight test engine for the A380. He's received Airbus's Excellence Awards, voted top 20 AM influencers in 2012 TCT magazine, which is really cool from someone who has been, who sees TCT as the place that really knows what it's about in this industry in terms of publications. It's quite the honor. And was responsible for the introduction of the industrialization strategy for AM and EADS over the past 10 years. So recently returned to aerospace sector with GK Enterprise after 3 years in motorsport on the Bloodhound SSC. That's the cool thing, 1,000 miles per hour car, land speed record. That is so cool. And was the whole thing printed? We wish, huh? And to my left, Eric McDonald. He's PhD, University of Texas, El Paso. And these guys do some fantastic work down there in the additive community. They've really pushed the envelope when it comes to embedded sensors. He's got some interesting examples that he brought with him. I had the honor of being able to go down there in November and visit and see what they were doing firsthand. And what they look at is the things that most of us would probably miss. Some of the really significant details that would stop anything that you would want to do. Because I look at additive, making the part. They look at the details of if I'm going to print a circuit, how do I do that in a microscopic way within the additive environment? So it's really, really advanced, futuristic thinking, but it's what needed to be done. It opened my eyes up of things that you might not think of. So he's also had a spin at being an entrepreneur and successfully sold that business. But again, surely let Eric speak a little bit more to his strengths on that side. But good operation going on down there, doing some really exciting work. And Paul, coming out of Ford, did you work with Doug Mitchell?
Yes, I did.
So Paul leads the section supervisor of rapid manufacturing Ford Motor Company. They have been a brilliant leader in this industry for many, many years. I've known the people at Ford through the Rapid Prototyping Association. Early 90s, they were committed to the technology. One of these days, we're going to see them printing parts for the engines. We just have to get up our production rates. So, and I think that you could probably speak to that a little bit, but what I hear, and that really is the issue. We need to kind of get the throughput up if we're going to be competitive in that kind of an environment. And that's a changing landscape, and we'll see some things good come out of it. But to know that you worked on the Ford EcoBoost, and I just bought myself an F-150, and it has the EcoBoost in it, and I love that truck. So it's pretty cool. And he also instructor at the Tech Shop Detroit, holds a BS degree in mechanical engineering from Kettering, MS mechanical engineering from University of Michigan Dearborn. So with that, so what I'd like to do is I'm going to ask each of the panelists a question. I've got a set of pre-recorded questions here, and I'm going to go have a seat. And then we're going to get started with some presentations too. So I want to do that. You're first, right? I gotta face the other way because that's the way I set it up, so. Did I go out of order a little bit here? It's okay, it works.
Well, again, good morning, everybody. I'm Bill Flight. I'm the Senior Manager for Advanced Manufacturing at Lockheed Martin. I work out of our Corporate Engineering and Technology office. And it's a real pleasure to be here this morning with this distinguished panel, but also with all of you. I wanted to just keep my opening remarks kind of brief so we have more time for questions, but did want to talk about what we're doing at Lockheed Martin. We've got 60,000 engineers and scientists across the corporation, and we are actively deploying additive manufacturing across all of our business areas. A few examples, we've got additive manufacturing in uses for rapid prototyping, for creation of tooling in our factories, all the way up to fielded and flown parts on some of our production programs. We see additive as a disruptive technology. We've been actively utilizing and driving additive for at least 25 years across the corporation. We've got some examples. We're heavily invested in both additive metals and additive polymers, both from being able to use commercially available technologies and equipment, but also doing a lot of internal development more on the polymer side to sort of experiment with how we might use what we call point-wise composition, but be able to change the material makeup as we print, so throughout the body of a structure. So if you can imagine starting a part that has, it's maybe thermally conductive and structurally soft, and as you go through the actual geometry of the part, that changes and is optimized for the control of that part. We're looking at it to significantly reduce cost, obviously, but also cycle time reduction and innovation from a design perspective. We are a strong partner with America Makes. Jim mentioned we recently signed a 5-year, $2.5 million commitment to America Makes because we really believe that having a national or an industrial commons around additive manufacturing is really going to move the country forward. There's a significant amount of research and development we're doing internally and with some of our university partners, but frankly there's a lot that we all can share out in the industrial domain. Sort of along the lines, all ships rise with the tide. Some basic fundamental research, primarily in material characterization, that again we can all, any of us that are looking to deploy additive, are looking to overcome some of those challenges. But again, we've got some extraordinary work going on. We've got partnerships with Eric and his folks down at UTEP, doing some brilliant work in additive printed electronics and embedded systems, heterogeneous additive manufacturing, if you will, where we're printing structure and we're embedding printed electronics as part of that. So it sort of really makes you take pause. I think it's a disruptive time in the industry. Being part of the aerospace and defense industry, we've had about 100 years or so to optimize our products around conventional manufacturing technologies. And with additive, it sort of flips everything on its ear, and maybe we'll get a chance to talk a little bit more about that during the panel. But from an engineering perspective, some of the fundamental principles that many of us who have been in the industry for a while, sort of the design principles, the producibility guidelines that sort of become our toolkit for how you design. And I have a background in spacecraft structural design and composite design. Some of those fundamentals you take for granted kind of get thrown out the window when you look at additive manufacturing in terms of some of the design techniques and producibility concerns that are driven primarily from conventional manufacturing methods that sort of go away when you start looking at additive. So we're excited about that, and again, it's a pleasure to be here, and I look forward to the questions from the group.
Thanks, Bill. Don, you want to jump in there?
So I have a presentation, if you can flick the slide over on that. Okay, GKN Aerospace, that's what we do. We make things fly. And I was invited to come today, and I flew on a 777, which was a new experience for me, as I used to work for Airbus. So I thought, as you probably tell from my non-Indigenous accent, I'd just start with a bit of geography. I'm not actually from from England. There's a very small island called the Shetlands just north of there, which is why I'm not actually comfortable speaking in front of lots of people, because I think you probably represent the entire population of the Shetlands. So it's known for being very cold because it's so far north. It has some fantastic landscapes, good fishing, some strange wildlife, the Shetland pony, and of course oil, and that's principally why I was there, because my father was in the oil industry at that time. So historically then, my background is in product engineering, and I've always had, or was fortunate in the early 90s to come across a laser sintering machine at university, which kind of was a catalyst for me to realise that everything I'd learned at university kind of went out the window. And I then went into industry and started with single crystal castings for the Trent 900 engine. And we introduced rapid prototyping, rapid manufacturing methods to enable the Trent 900 engine at that time. So it wasn't direct manufacturing, but it was what I recognise as a very early value stream in a product environment. I then moved from engines to aerostructures and worked for Airbus for a long time. The picture in the middle there, Airbus A380, was my first aircraft program. And staying with Airbus, the A400M was the most recent one I worked on. And we used AM on the A380 to actually get it through its certification program. It had some issues that were only resolved because of the speed at which you could respond in not just your process, but also if you understand AM and you understand the design, then you can actually quite quickly resolve problems quickly. Although they were only temporary solutions, we qualified some ducting on the wing for 400 hours, so it actually worked really well in that case. I then decided to move into motorsport and worked in F1 for a little bit, and there's lots and lots of application range there. Big difference there for me was scale. So there was obviously a lot more interesting AM applications. And then the Bloodhound car, which some of you may have heard of, but that's a supersonic land speed record car which is being produced now. That's got a rocket and a jet, and will hopefully be out in the desert testing in 2 years' time. So in November last year, I returned to aerospace as Chief Technologist at GKN Aerospace. And just to give you an idea of the size of GKN, having come from EADS corporate before, which was about 125,000 people, GKN feels quite small to me. Although it is a global company as a PLC, if you like. It's got 4 divisions. The biggest division is in the automotive and the powder metallurgy. The land systems and the aerospace is really a newer division for us historically, and that's where I sit in there. We've grown as a company through typically acquisitions. So we bought Volvo Aerospace and some Airbus and some Boeing interests at a sort of, because we're a tier 1, and that got us into the aerospace market. So product-wise, we're pretty much across aerostructures and engines. The business mix there, as you can see, the badges, the logos there. As a tier 1, we've got quite a diverse range of components that we make for the aerospace industry. It's about a 50-50 split between aerostructures and engines. But if you can sort of imagine the scale of the different kind of products that we actually do, it makes quite an interesting application range potential for AM. I'll come back to that point shortly. Typically, we've been a manufacturer as a tier 1, and we're now actually moving through a process to actually increase our engineering and our design authority. So in the future, we'll be able to develop technologies with design authority and materials and process qualification. So one of our first programs that I'm involved in is a sort of a global engineering program around putting an R&D program in place. and that focus is very similar to the NAMI MRL process. So we actually pitch ourselves between academia and production. So we sit between TRL 4 to 5.99 reoccurring. The day after that, it's handed over into the business. It's not quite as serial as that. We obviously work very closely with academia and we work very closely with production. I think that's the important bit when you're working in that phase. We have 3 centres that all have additive manufacturing. One here in the States in St. Louis, Sweden, at Trollhättan, and in Bristol in the UK. And within those centres, we actually have capability as well. So we work across the nozzle deposition processes, be it EB wire, plasma wire, etc., and powder bed technologies, principally in metallics today. We've resolved that actually even further, just to make it even easier for my grown-ups around me to understand. Big puddle, small puddle, and powder bed. So where I sit in Filton, we have a qualification program around electron beam melting, and that's reached TRL4 with our customer Airbus on a project there, so that's coming along really well. We have a fairly conservative approach to introducing the technology. So the new stuff that everyone talks about, and you'll go to lots of conferences and see really super cool, multifunctional structures and materials, and that of course is in our R&D portfolio and is our vision, but we actually have to start somewhere and start delivering value to the business. So we actually start right down the bottom left and just try and trade existing components for AM1s. Along the way, we'll introduce new design thinking around that, topology optimization, new microstructures, etc., and just grow through that period. We're quite new to this. We've only been involved in AM really for 3 years. Of course, all the values that you'll note from various conferences, the moving to design for application is the key thing. So trying to deconstrain your product from locked-in downstream costs from manufacturing. Where can we explore much earlier in the development of components and product and actually design more functionality in the components. Here's something I took a shot of just before I came out here. The component in the middle is an existing bracket for an aircraft. The bucket of swarf on the right as you look at the screen is from the machine billet, and the bucket of swarf on the left is from the final machining of an AM. In terms of the difference, what we call the buy-to-fly ratio, you can see there's been no change in the design of that part. The value we're looking at here is purely on cost reduction in material, and it's quite a strong business case when you consider 13 times less swarf, 5 times less raw material feedstock. So if you can get the cost out of that end of the materials, you actually really will unlock some very early components. In terms of the future, that's A380 wing. In terms of scale, those are one-to-one scale people. In my mind, when I was in Airbus in those days, I was looking at that and thinking, how the hell am I going to get additive manufacturing on an aircraft? And that was in 2000 when I was playing with stereolithography. So there was a huge challenge there. I think it speaks for itself. You've got to start at the smaller scale components and look at where you can enable more value, so the topology optimized components like these. If you go down the length scale in terms of material, you get down into the micro and the mesostructures, and you get the mechanical or tailored mechanical behavior you see in these lattice structures. That gets quite exciting, but it does promote other areas of research that need to be done in terms of other technologies like the analysis and the design tools. Without those being developed, you won't actually get this value, even though the manufacturing technologies theoretically can make. If you keep going down the length scale, you start seeing cellular printing. Talked about printing food before. Printing organs is in the news. If you keep going down the length scale again, you kind of arrive at the Star Trek replicator. That's on Wiki, so don't believe me. For us then, just to round off, I look at this as more of an integration of not just the hard physical technology or material, but also the business processes around it, the people, the training, etc. And this is kind of a bit of a brain dump from myself on the flight out, just to sort of try and articulate where we think we are today. So we know a lot about the process. We've got a fairly good handle on some material. We can design with using today's technologies, but there's a whole space that we haven't really developed yet. And I think, can we find application and business opportunity today with what we do know? And then how do we push those borders out and acquire knowledge in the future to unlock those large-scale whole wing structures in the future? So that's me, GKN. Thank you very much.
So I thought that as the university representative here that I would be the blue sky guy, and Dan just brought up the replicator. So I guess I'm going to be pretty conservative. I got a presentation. It should be pretty brief and hopefully entertaining. And so I'm going to describe 3D printing multifunctionality, which is an area of research we're working on. So do I need to do the slides, I think?
Yeah.
Yeah, okay. But before I do that, I'm going to just quickly give you an overview of our facility. I'm from the University of Texas at El Paso, which is closer to Los Angeles than it is to Houston, to give you a geographical reference. It's not Shetland, but it's close. We have about 13,000 square feet, 47 different systems. We can do metals, ceramics, plastics. At any given time, we have about 50 faculty, students, staff, postdocs, research engineers. And essentially, the overarching theme of our center is that everything we do has to do with additive manufacturing. And I think one of the things that sort of sets us apart is that we're very multidisciplinary. I'm the associate director, and I'm an electrical engineering professor. I'm originally a chip designer from Austin, and we have metallurgists, materials scientists, computer scientists, and in a world that's normally dominated by mechanical engineers, we have a wider mix of people. And I think it's really the intersection of disciplines that brings to bear the more interesting research. And what I'm going to talk about today is one of those areas of the many that we work on. And it's what we call 3D printed electronics, or 3D multifunctionality, where we take a 3D printing and we interrupt the process. And we integrate into it other complementary manufacturing processes like micro machining, micro dispensing, pick and place. We embed wires, we do laser ablation, anything we need to do to add functionality to the structure so that it's not just a mechanical structure anymore. So this picture shows on the bottom left a 3D printer, for instance. On the top left, these other technologies that we would integrate together. And then to the right are these projects that we've done over the last 15 years that I'm going to describe a couple of today. And so of all the different 3D printing technologies that we've looked at, what we've really converged on is materials extrusion, specifically thermoplastics, because they tend to be very functional and good for end-use products. But more than that, we've also discovered that we can ultrasonically or thermally embed wires down to like 80 microns into the thermoplastics, and they will submerge into the thermoplastic, leaving a planar surface where we can subsequently fabricate more dielectric above that. And so this picture shows, well, first off, we can introduce these electrical interconnects and meshes, which can act as ground planes. We can do pick and place to put a microprocessor, a sensor, accelerometer, whatever we want, into the structure as we're building it. And it can be in any arbitrary form, intricately detailed, complex geometry. And then we can laser weld the components together. And essentially what we're doing is making a 3D printed circuit board with relatively good performance, with wires giving us bulk conductivity. And then we discovered there's sort of, well, serendipitous advantages to this. If you put a mesh of wire into a thermoplastic, it basically becomes a composite, and that you improve the mechanical properties of that material, like putting rebar into concrete, for instance. Another thing was we essentially invented capacitive touch sensing, so that now we can print a handle, and you can touch the handle, and it can sense that you're touching that handle. Or we can do microfluidic channels and sense that water or salt water or gasoline is going through that fluidic channel just because of the capacitive changes. So some interesting applications that you can do in the context of the freedom of 3D printing, right? And that little video shows a real simple example of capacitive touch sensor. And then, okay, this is the first version of sort of the Holy Grail 3D printer. This is two different Stratasys legacy 3D printers that are tied together with a conveyance system at the bottom. You can see that we're doing material A right now. We can go over and register for material B. And then when we want to do these other complementary manufacturing technologies, we go to the bay to the right. Now we can do pick and place. We can do laser ablation, micro dispensing, micro machining. We can embed wires. So this machine conceivably could be your replicator. It could create a CubeSat. It could create your new iPhone, right? It could, I mean, I'm being a little blue sky, I guess, as the university research professor, of course, but at some point, inevitably, we will be able to print your iPhone that you'll download to your house, and it'll be custom fit to your hand, would be an example. Or again, a CubeSat, or a UAV that could fly out of this machine. So just to give you some demonstrations that are, I guess, in the context of this conference, appropriate. We've got certainly lots of UAV applications we're working on, but about 4 or 5 years ago, one thing we did was we did a wing of a UAV where we embedded into the wing prognostic ability of doing a strain gauge. So a lot of people will use the catchphrase for 3D printing that you get complexity for free. Well, one of the things we're pushing with this technology is that you get the electronics for free. You build a structure, and we can embed the electronics inside the structure, essentially for free. And in this case, the strain gauge would be actually monitoring the health of the wing, and it would just be embedded within the wing as it was being built. So in November, we launched a CubeSat with the University of New Mexico called Trailblazer into low Earth orbit. We believe it's the first time 3D printed electronics have been put into space. A sister piece is on display at the London Museum of Science. We're hoping to go see that in a couple of months. That's actually farther from El Paso, I think, than low Earth orbit. I'm not sure which is farther, but depending on where it is. But certainly we have a lot of interest in trying to get these 3D printed applications into space. And Jim had showed a picture of Made in Space. Jason Dunn, the founder, was here yesterday. We're working with those guys pretty closely. They're interested in being able to print CubeSats, and they've got a 3D printer that they're putting into the International Space Station. And so there's a lot of interesting applications. And then one application which is getting a lot of attention, this is kind of a quirky idea, but the idea that everything we had done before had no moving parts. But really what we want to do is to be able to do, like Oak Ridge had the pneumatic prosthetic titanium hand. And so I went and saw those guys, and it's just an amazing engineering feat that they've done. So we'd like to be able to print a prosthetic that has the actuation built into it, or a motor, or a linear actuator, or a wide variety of moving parts. And so we had an undergrad that decided he wanted to design and build in a seamless, non-assembly process, a DC brushless motor. And so in a U-print, which is a cheap Stratasys machine, their lowest end machine, he basically interrupted the process and manually inserted at 6 different pauses, which are shown here in these pictures. He inserted components and then wired them together. Now, all of this could have been done with automation with that machine I just showed you, but of course, for a university, student labor is a lot cheaper for us, right? And we're just trying to get a proof of concept. But we have a time-lapse video of this 6-hour process of building the motor, and what's cool is that he pulls it out at the end, and it's working at like 8,000 RPM. And so I'd like to show that to you. And so this is just a $20,000 low-end Stratasys printer. Not that that really matters. We could have done it with a MakerBot, or we could have done it with a Fortis, $500,000 system. But this was what was available to the student. And this guy is going to be working at Oak Ridge National Labs this summer. He's a brilliant student. So it does, it seems like it's a little choppy, but so the orange is the thermoplastic. Now he's putting a ball bearing in, so it's going to have 2 structures, the rotor and the stator. There, it's getting a little better. And this usually takes about 6 hours, so you're getting the quick view. Now he's going to manually put the magnets in, but of course this could be done with a pick and place machine easily. It's just for a university professor trying to publish papers. This isn't very publishable, right? So let the undergrad do it. The coils, the electromagnets, we're treating those as components. And then the actual insertion of those he's doing. The wiring would be done with ultrasonic embedding normally. Right here it's being done with conduits that we've designed in that he's manually inserting the wires into. Unfortunately, the video is not very, it's a little choppy. But when he puts the part back, it's registered so that it's going to be in the exact same location. Now it's going to go ahead and top it off. He puts a second ball bearing, which then has 2 free-floating structures. It finishes, and then he'll pull it out and run it. Normally, the video is a little more fluid than this. So he plucks it off the platform. Oh, it's stuck now. I promise you it works. I don't know, the video appears to, oh, now it's starting over. Yeah, is there any way you can go to the very end? To the triumphant. Yeah, well, I think it's embedded is the problem. It might be. Yeah. Is there any way you can push it forward? Well, in any case, yeah. This video is on our website if you want to see it. There's a couple versions of it. It's pretty entertaining, I think. He's a real cute kid, too. I shouldn't call him a kid, right? I mean, as a professor, I should. He's a very hardworking, diligent student. Yeah. Let me go to the final slide then. I've got 10 minutes. And I've got some examples here you can see too as well. And then finally, I just want to point out that our university, which of course is in the middle of West Texas, has got the only example of Bhutanese architecture in the Western Hemisphere. And if any of you happen to be in El Paso, which probably doesn't happen very often, but if it does happen, you certainly have an open invitation to come and get a tour of the lab and have some research discussions with us if you have ideas. And certainly it's worth seeing the architecture, which is strangely well suited to the Southwest landscape. And that's, okay.
got a few notes just to keep me on track. I'm very passionate about this subject, and I could talk for hours. As Jim mentioned, this isn't a new technology, and Ford's been in it since the beginning. Larry Ellis, friends with Chuck Hall, right? We've been in it. We bought stereolithography serial number 3 from 3D Systems. Ford's been entertaining various companies. We've been working with them over the years. We've helped them develop their technologies, their machines, their processes, getting them robust. One example of that is 3D sand printing. Back in the right after the turn of the century, Ford discovered a couple of gentlemen in Germany working in their garage with an MIT patent to try to sand print some casting molds. With an MIT patent, there's some issues, right? So Ford got involved. This is a technology that we want. We want to be able to make castings very quickly. It's a big part of our business. Ford got involved, got our attorneys involved. We hooked them up with a company in the United States, helped them to understand what robust manufacturing of a machine is, and now you can go out and buy one of these sand printers. So Ford's been heavily involved for the past 25, 30 years as 3D Systems. Ford has 5 labs, 5 commercial labs. I run one of them. We don't work for the same directors. We don't work for the same VPs. We don't work in the same organizations, but we work as one Ford together in a collaborative mode. Give you an example of that. When we create a machine that goes into production, we have to run several parts on the manufacturer's floor first to make sure that the machine is ready to go into our plants. There's a machine in Germany right now that puts the adhesive strip around a moonroof for a new vehicle. The engineers over in Germany and in the United States came to us and said, we don't have any parts. What can we do? So we brainstormed with them and came up with an idea. And my lab is rapid manufacturing, which includes additive, but it's got some other technologies as well. We came up with an idea to CNC machine out of Renboard, which is a composite, the basic structure of the roof. And then because the wear parts where this machine was going to touch, we were going to investment cast these parts out of aluminum using 3D printed molds, or not molds, but actually sacrificial pieces for the investment casting. Because of the critical time nature, this has to be done very quickly because they're right up against the delivery date for this machine. I contacted our lab over in Dutton, England, said, hey, Richard, we've got a project for you. We've got some data. Let's collaborate on this. We sent them the data, worked with Richard on the design of the investment castings, and he's creating it in England to ship to Germany. So 3D printing, as it's all known now instead of additive manufacturing, as we call it, is really helpful in being able to bring the world together. So why use 3D printing? Over the last couple of days, I've been listening to folks in the aerospace industry talking about their development time getting longer and longer and longer. And I think I heard one gal, she told me it's up to 15 years now to go from concept to what we would call production. Ford has a similar issue. If you look back in the 1960s, it took us about 7 years to go from concept to job one. Well, the market and competition said, we can't have that. People want cars faster. The competition's doing it faster. So if you look at where we're at today, we can do it in about 1/4 of that time. And one of the main technologies to be able to do that is additive manufacturing. So where do we get the additive manufacturing? What do we do with it? So the first thing we do is the engineer comes out and says, okay, I've got a part. I've got an intake manifold, let's say. Very complicated geometry. There's a lot of flow dynamics, computational fluid dynamics involved. I've done my model. I need to test this part. He comes to us. We make him a very accurate 0.5 thousandths per inch accuracy part, which is within our manufacturing tolerances in the plant. He takes it away, does this flow analysis. Comes back, said, yep, that's exactly what I want for the runner design, but I don't know what my final part needs to be. I've got constraints. I've got 6 or 8 different ideas. Well, in the old days, he would have to make tooling. Make that part, traditionally, maybe go injection mold that part. It'd take 3 or 4 months to make tooling and several $100,000 to make one trial. After that one trial, he'd make his tests and make a decision. He said, well, I've got one more shot here. I've got to make some changes. He'd only get 3 shots in a serial fashion. He comes to us now with 6 or 8 different ideas. We make them for him very quickly. Make them for him in a couple of days. He can then go back in, test all 6 or 8 different designs, come back to us and say, oh, all the data now for those 6 or 8 designs, and I've learned something. I've learned a lot of things. I've got 3 more designs that look nothing like the first ones. I need these now. So we'll print them for him again. So now he's got more information. We do this time and time and time again. So he can have, instead of those 3 trials at engineering that part, he can have 50, 60, 80, 100 different times to refine, optimize that part to get it to exactly what the customer wants. Plus, in the meantime, he can work with his colleagues, bring the parts to meetings, collaborate, find out what the parts are that are adjacent to that part, make sure they fit. So at the end of the day, he says, okay, I've got my intake manifold. It's exactly what I want. It makes the power and everything else, the fuel economy that I want. But now I need to just double check some stuff on the flow dynamics that I checked before, and I want to confirm some things. So we'll make that part clear, which I can do in 3D printing technologies, instead of machining it out of acrylic, which was very expensive and time consuming before. Then you can go and use some of the technologies you'll find downstairs with lasers, et cetera, to do double check on the flow. So it shortens the development time with no tooling. So you get the speed and the lack of cost and the lack of design time for that tooling. One of the key technologies at Ford is 3D sand printing that I mentioned earlier that we help to develop. We do, as Jim mentioned, he's got an EcoBoost F-150. All of our EcoBoost motors were developed using additive manufacturing technologies. The speed with which we have to be able to develop these engines is very, very short. So if you think about EcoBoost engines, they're a very high power density engine. They're direct injected, they're turbocharged. You as a consumer don't want to step on your accelerator and have turbo lag. You want it to act like a much larger engine. In order to do that, we have to close couple the turbocharger to the cylinder head. So one of the things that we've done in Ford is there's no longer an exhaust manifold. It is bolted directly to the cylinder head. The exhaust gases are integral, and then they come out right at the turbo. That presents some very stringent thermal management problems. So in a traditional manufacturing development project, where I might only get those 3 stages because it takes me 4 months to create my first part, I'd never get there. So again, product engineering does all their computer analysis and design, figure out what they think they want. They come to us. We quickly print the molds, go to the foundry, pour their castings, and we make those castings like production. I have parting lines in the right place. I have my draft angles in the right place because, unfortunately today, I can't print every single one that's going to go in production. So I have to understand what that part's going to be. So through that process, all of the EcoBoost engines now have much higher quality, performance, fuel economy than we would have been able to do otherwise. In fact, even the new 2.7 liter EcoBoost that was announced in the new F-150 just earlier this week was done using those technologies. So let's talk about production now. We've talked about how we get there, how we get to the product, but in production, we have the same issue. Once we have a design of a product, how do we then produce that at 1 part every 12 to 18 seconds? Well, I can't do that with the technologies today, unless I've got a very small part that has to be designed in a specific manner that only 3D printing can do for the automotive industry. For aerospace, with the much lower volumes, it'd be much easier to go into production. However, I can still shorten that development time, because once I get the part done, now I've got to make the tools and the machines and everything else to go and produce that part. I can make the tooling that make the part using additive manufacturing technologies. For example, if you have a hood for an automobile, say a new Fusion, there's a press line that stamps out that hood out of sheet metal. There might be 4 or 5 presses in the line. On the bed of each of those presses are several specialty castings that stamp the shape and cut the material. In the last press, I've got the shape of the hood and I've got a lot of extra material around it. I need to get rid of that. There's a set of die steels, die cutters, that cut off the extra material and then cut it into smaller pieces to get rid of it. There's about 50 to 70 of these parts on a die. Each one is unique, not only on that die, but is not common to any other vehicle. So what's the best way to do that? Well, the old way was not very accurate because of the processes. So it took 3 to 5 days to machine that part to get it to where it needed to be. With additive manufacturing processes like 3D sand printing and the CAD that we have today, I can take that part, make it really close to that shape, and take it from when I receive it into my die shop, I can have it on a die and ready to go in about half an hour. So, plus the whole time from acquisition to, or from order to acquisition is about half of what it used to be. So think out of the box. These parts that we're putting now into tooling, you know, engineers come to us the first time and say, well, here's my design, go 3D print it, or 3D print the mold and then cast it. And we go back and say, well, you've designed it exactly like you did the old part. And it's just, you have to think out of the box. How about form meets function? Design this part so that the stresses are handled where they need to be. Reduce the weight, get the strength up and the weight down. Now there's a domino effect, because the part that's holding that tool can now be lighter. And all the way down to the total machine now can be smaller and lighter, reduce cost, save time. So it's a whole mindset change within the company. My particular lab makes about 20,000 parts a year for a prototype. Ford's, in its history, and it's starting with 3D systems, is probably about 500,000 parts today that we've made using additive manufacturing technologies. And the technologies continue to change and advance, as these gentlemen here have even told you, right? There's more materials, there's more technologies every day. Companies are going public now that were private before to get revenue to be able to create new technologies and bring more to the party. So at the end of the day, where can you use additive manufacturing? Basically, it's everywhere. In your research, you know, my facility not only is the prototype factory, so to speak, for Ford Motor Company, we also do a lot of research. We have the naysayers, as a lot of people say, right? You'll never make a cast-in liner cylinder block in a lot of one that's anywhere close to production because you need this $500,000 piece of equipment to do it properly. 2 years after that naysayer came to us and told us that, we can now do a cast-in liner block, lot of one, no tooling, 3D printed molds, and it's at least as good as production. So think about it for your research. Then think about when an engineer has a part, I know your industry is probably like ours. People like to hold their designs close to their vest. Print it. Give them something in their hand that they can take to a meeting and collaborate with and actually try to bring it to market. Once it's 3D printed and using those technologies, you can optimize the design. Keep going. Make multiple things at one time. Print it. Bring it out. Refine it. Optimize it. And then if it's not going to be a 3D printed part on your vehicle, then you think about using 3D printed technologies to make the tools and that to create the parts. So other than that, that's my perspective, and I look forward to answering questions. Yep.
Mic on. Paul, thanks.
Yep.
Is that mic on yet? It is on. Okay, thank you. So, you know, the session is about this additive manufacturing being a transformative. You know, for quite some time we've looked at it as a disruptive technology. And I think what I'd like to do is assemble a group of questions here, or Ed Morris did, and they're great questions, and I'd like to direct them to each of the panelists and then get comments from the panelists to their thoughts across the board, and then open it up for dialogue with the audience. We have a little less than 50 minutes before lunch, so we want to get it on and make sure that you have a chance to answer your question, or ask your questions. There's a mic in the center of the aisle here. So I'd like to begin with putting my first question to Paul. The question is, for a technology that has been evolving over the past 25 plus years, there has certainly been a lot of media hype about 3D printing during the past year. From your different perspectives, and of course we'll open it up, but I'd like to get Paul's first, What has prompted all of the media attention, and is it merited?
The media attention today, I think, is driven by the personal use computers, the MakerBots and that type of thing. The technology has been around for quite a long time, but nobody really knew what was here because it was in industry. As the patents are running out and have run out on various technologies, and companies like MakerBot start to produce something for the consumer, it's getting a lot of press. In fact, the Ford Motor Company, and my lab in particular over the last year, has probably done 30 to 40 media events with reporters from magazine, TV, radio, and they're all very interested, and most of them that come in think it's brand new.
Yeah. Right. Thank you. Eric?
I just want to add something to that. That's definitely the reason, but there's a couple other things too, like the gun that there's been a lot of applications that are sort of out there.
Well, I think, printing the Stradivarius
the
was,
Stradivarius.
one of the first things that really,
The musical
went across the wires.
instruments, the dress. I know there was a fashion.
Right.
Yeah, there's just, that, and then the democratization by MakerBot, the lowering of the cost.
So the question is it hype, or is there substance to it? Anyone else has any?
Yeah, I'll just make a comment. I think obviously the hype is there, but I think the hype is warranted in the sense of, it's brought a technology that's been around for a long time, and it's brought it to consumers. And in a lot of cases, we in the aerospace industry don't get a chance to benefit from that. Typically, it developed an industry and eventually makes its way into consumers. This is kind of maybe, our benefit is going the other way. So when you look at the hype of being able to print jewelry, print parts and show them to your friends or sell them on Etsy or eBay or Craigslist, there are literally no barriers to doing that today. But there's a big difference between doing that and printing parts to put into a manned spaceflight program or onto a fighter aircraft. So when we talk about hype, is the technology, is it really all there? It certainly is, but we have to be conscious of the application of where it's going to be used. And I think we in the aerospace industry, we have to be really cognizant about trying to leverage the technology for as much as we possibly can, but recognize that some of the covers of The Economist and some of these other magazines, they're targeted towards a consumer community as opposed to an aerospace and defense community.
Right. It's the industry has really benefited from. A lot of it can be traced back to the president's speech a couple of years ago, State of the Union, when he mentioned 3D printing. And there was a lot of attention all of a sudden given. I mean, from someone within the industry, it was amazing what that conversation with America had on our industry. And a lot of people senior leadership in companies started to ask their business, their people, do we have an additive manufacturing strategy? I'd never heard of that prior to it, but it's pretty commonplace today. And the fact that we have printers now below $1,000 is really a driver, a catalyst for democratizing the technology. And it doesn't matter, where the printer's made. It's happening in a lot of quarters, and there's a lot of diversification of product coming out there, and a lot of different applications. So I think that's added a lot to the reality of it. So question: is it hype? Is it hype is a negative word? Is it real? There is a lot of hype. I mean, let's not kid ourselves over what there was 5 years ago, 3 years ago. There's an immense amount of noise and volume out there about it, and that's all good stuff. I think the questions will come around from a manufacturing standpoint. Is it hype, or is there something of substance here? So we'll engage in that a little bit.
Just to add to Paul's comment, that I think the hype has been driven by the domestication of 3D printing. I actually banned and made it a sackable offence to use the word 3D printing in Airbus. It was because about perception management. And when you're in industry, if you're going to talk to a manufacturing director about rapid prototyping, as I was doing in the late 90s, you'd often get an email back from the PA saying, it's not rapid and we don't do prototyping. So there's a branding issue, I think, associated with some of the terminology. So I think the hype has been driven largely by the adoption at the domestic end. I think we have to be careful at an industrial level that we consider additive manufacturing in a completely different way. So if you look at some of the data that's published around the size of the market, that's actually mixed with the domestic and the industrial. And actually, if you resolve that picture, it's probably nearer to only about 10% is actually industrial application than the $3.5 billion industry that we see today. The other point is I made a comment recently about that we're moving away from innovation into qualification. So be it after the hype cycle, on the dark side of the moon, if you like, of that hype cycle, I think industry will go rather quiet. You won't see much in the way of innovation because we're all going to be heads down qualifying stuff.
Right.
So,
Which is, to me, it's really fundamentally where we're at because of all the attention that's been given to it. A lot of it's been outside pressures, but the fact that we're seeing materials people come to the table that were never interested in the technology before. There's innovation on materials, there's innovation on technologies. There's a lot of attention now be given to qualifying the various processes and materials so that we can transition into production. The pot's filling up. It's getting, fuller than it's been in the previous 27 years, I can tell you that. So, good. Any questions from the audience that you'd like to ask the panel on this? Please give your name and your organization.
Good morning. My name is Justin Kaiser, and I'm a PhD student at the Aerospace Systems Design Laboratory at Georgia Tech. And first off, I want to just thank the panel for the wonderful presentations and discussions that we've had so far. It's been really engaging and eye-opening to myself, and I know everybody here. So the question that I want to ask is, we've talked a lot about today at how additive manufacturing can be revolutionizing the manufacturing process here. But what I would hope to open to the panel is what your opinion is on how additive manufacturing could revolutionize the design process. So where we've traditionally been waiting in aerospace, we move through, I guess you could break it into conceptual, preliminary, then detailed, and then finally go into production. We typically wait until detailed design to start cutting metal because that's when it's, things have been set and it's expensive to do that. But now with this technology, if we can eliminate the tooling, if we can do that with that kind of speed, what does that mean that we can now bring to the preliminary design phases and prototype high-risk parts before we have to set things in stone and wait till later in the design to do that?
I'll take that one. I think it's completely disruptive. I think it's going to put our design process on its ear. We've been researching how we can use agile design processes now for hardware development. The software community's been doing it for decades, right? You build a little code, you compile it, you test it, you debug it, and then you build a little bit more. And you have this iterative spiral development that we in the hardware community have been jealous of for a long time, but the nature of how long it takes to build hardware doesn't allow us to do agile development. Now you introduce additive manufacturing, all of a sudden you can do quick builds, you can do sprints, you can make throwaway parts just to get, we call them limited limited engineering units, but they could be as simple as building something that just, allows you to visualize, bend for a harness connector or something. But it's throwaway parts. So I think it really has the opportunity to transform how we do development. We're starting to measure ourselves not on the sort of the conventional, you do concept, you do preliminary design. By PDR, you have a certain percentage of your design complete. By CDR, you have 80%, you start creating drawings. And that's historically how we've measured maturity on a program. But when you look at using additive manufacturing, you can use it as a risk mitigation. So you can do some high risk development, prove it out through additive manufacturing, do some prototyping, retire risk, and then actually pull your design reviews in many cases. We're finding we're pulling our design reviews to the left because we've mitigated all the risk. And and that's before typically we would go into limited production. We're able to do that now before we even get to a design review.
Perfect example that at Ford, as I say, we use the technology quite a bit all the way from the initial design phases. But even in our research facility, we will make engines that you will never see as a consumer. It'll have 50 to 100 different advanced ideas that are way out there. Some won't work, some will. We'll build engines with those technologies very quickly and inexpensively compared to the old methods, and we'll test them. And it's a great time to fail. one of the things that people say, fail early, fail often, right? Because what you fail on, you learn something from it. So we do a lot of that type of work up front, and I would encourage pretty much everybody to do that. I mean, it's a great idea, and it's inexpensive and quick.
Derek, you want to?
And maybe just one more comment. I mean, maybe you're thinking about this from a mechanical engineering standpoint, but what about a multifunctional standpoint where the electrical engineering, the mechanical engineering, or the fluidics and all these things, well, I guess an engine you're dealing with that, but now we've got to take it another step where more multidisciplinary aspects have to be integrated into the design effort earlier. It's, yeah.
Right, you can tackle the systems engineering integration aspect a lot earlier.
Exactly, yeah. What we design now is we're doing it very barbarically. It's graduate students doing manual work.
Don?
I think it's actually a really difficult question to answer because unless your baseline is assuming that the product you're talking about in terms of overall design is fully AM enabled. Today, I look at components as really just a set of interdependent variables as a whole system. So one of those could be really enhanced using AM, but there'll be a lot of other components that are still conventionally manufactured. So it depends where you sort of orientate your thinking as a start point of that. Of course, if you assume that AM is the de facto manufacturing system for everything, then you can really change your whole design methodology. As a sidebar kind of comment, I think what we're sensing now is that design tools today actually are quite limited, and design analysis tools really need to move on in their evolution. There aren't any AM knowledge bases in CATIA, for example, as our design system. It's only recently we've actually had composites knowledge base modules in design tools, and that's 60 years after we started playing with composites. So in terms of design, I think biggest driver has got to be improving design tools.
Okay, thank you very much. Appreciate it.
Thank you. Hey, we have another one, please.
Hello, I'm Yasmin Tajde from National Defense Magazine. So my question is, it's a known fact that the defense and aerospace industries are struggling under budget cuts and sequester. Now that 3D printing seems to be really taking off, do you see that this is a way that it could revitalize the industry? And then my second question is, what kind of weapons do you think would really benefit from 3D printing? So we talked about drones, UAVs, maybe guns, mostly directed to Bill, but anyone else can chime in.
Maybe I'll start
Bill,
with the
please.
second half of your
I
question.
didn't hear the question myself.
Yeah,
Oh, you couldn't hear it?
I didn't hear it very well, I'm sorry.
Sorry, I'm short.
There you go, thank you.
The second question was, what kind of weapons do you think would really benefit from 3D printing? So drones or guns?
so we've got two examples, not weapons-based, but part of our sort of product portfolio. At a recent conference, we exhibited a fuel tank dome, a titanium tank dome that conventionally the way we make them is we get a titanium forging. It takes about 12 to 18 months to get the forging. We rough machine it, heat treat it, final machine it, and then we proof test it, and that's how we build them. That's historically what we've done. And you're limited on the size, you're limited on the cycle time. They have huge cycle times. And you're limited on the size by the die and press. You know, it can only build so much. We're actually now 3D printing titanium propellant tanks. And the way we're doing that is we're taking a 12 to 18 month lead time for getting forgings and printing the rough shape in 3 hours. So we're you know, even when you add in rough machining, heat treat, and final machine, and final inspection, we're taking a 12 to 18 month process down to a month at less than half the cost. That's one example. There's another example. We have lots of examples, but another one we're looking at. We're doing some qualification with SciTech in Chicago on F-35. You know, we've flown. We've talked about this on the Juno spacecraft. It's actually on its way to Jupiter right now. We've got additively manufactured titanium parts that we qualified and are flying, and they're actually on a space vehicle. But for, you know, that's pretty easy stuff, relatively speaking. It's secondary structure, wire, waveguide brackets. On F-35, we're actually qualifying primary structure, 10-foot long flaperon spars that are being made through additive manufacturing. Again, very similar scenario where you're replacing a forging that inherently has a very long lead time, And by using additive manufacturing, we're replacing a forging with a printed preform, that's orders of magnitude reduction in cycle time, just as a couple examples.
That's a good example. I had the good fortune of being able to see that, and it was 80% cost reduction and 50% time, or I may have it reversed, 50% cost and 80% time reduction. It was an amazing piece.
And those are just two examples that are very high visibility, but every one of our business areas is, to Jim's point earlier, along the hype side, we're starting to get questions now from program managers and tech directors on how they can use additive manufacturing to drive affordability into their programs, to increase quality and yield and cycle time reduction. It's transformative.
Thank you.
Thank you. So I'm going to go to, actually I want to skip the second question because I think we've covered it a little bit. The third question here, skipping two. America Makes is chartered, and I'm going to direct this initially to Dan. And America Makes is chartered to accelerate the use of additive manufacturing in the United States. To do that, we focus on the barriers to ubiquitous use of additive manufacturing. What are the principal technical and business barriers that you are encountering? And if you can share, what is your organization doing to overcome those barriers?
That's quite a broad.
That you're able to share, and of course,
Sorry?
that you're able to share, I think that.
Yeah. I think at a national level, we need more integrated programs, a little bit like what you guys are doing in the States here with America Makes and NAMI. We don't really have a national strategy yet.
Correct. Well, you actually are part of NAMI now, so I mean, because I think you were recently brought in as a foreign entity because you've gone through all the firewall gates and everything else, so.
Yeah, and ITAR, but I won't talk about that. So at a UK level, I think we need to get more of an integrated approach to the development of the understanding how to set out a research agenda for the technology, and then there's the skills and how you implement, and the qualification side of things is really the big elephant in the room all the time, particularly on safety critical primary structures that we're involved in. I think we should be looking at out of sector applications, so we're developing a large pool of knowledge and expertise on the process and the subject, but it might be smart to follow the history of what composites did. And it wasn't until they went into fishing rods and tennis rackets that a technology industry existed, and then went into Formula One, and it's grown to a scale so it's really about scaling knowledge and scaling the infrastructure around us, and how do we influence that. So that's all things that we need to consider really going forward. It's really about integration and collaboration now.
Good, thank you. Anyone else going to jump in on that? So, America Makes is chartered with looking at these big problems. And, the big industry problems, or the big problems that industry hasn't stepped up to really deal with. And I think that, qualification of process, qualification of materials are the huge hurdles that we have to make this more pervasive. We look at recent last 3 years, maybe 4, ASTM adopted a new project which is additive manufacturing F42. In fact, the name rapid prototyping was changed, hopefully forever, to become additive manufacturing. Of course, the media would have us refer to it as 3D printing, and I think most of us now, if someone asks me what I do, I say additive, they look at me like I got two heads. I say 3D printing, they said, oh yeah. So, I think we're kind of being trained to adopt it, what is becoming a norm, I think. But, so I think that, as an industry and as each company who's stepping in to participate in this industry, material suppliers, new machine OEMs, both metals and polymers, around the globe, what we're doing is looking at those barriers that we need to get over, around, and through that would keep us becoming pervasive. And I say pervasive, I don't mean just, I mean on the consumer side, and I also mean in the aerospace side, and in the automotive side, and everywhere. You know, we need to pull down some of the things that you know, would keep people from using it, mechanical properties that we need to have, databases that we need to have about known materials and processes. So they're the barriers that we'll take down, we're working to take down. Any questions from the audience on that subject, please?
My name is Andy Quas from Northrop Grumman Corporation. And we were doing a lot with AM and UAVs and satellites, work with Eric on 3U. I think a lot of the advancements in AM are really dependent on eventually getting out of just making brackets and actually getting into making things there will come a time where 50 to 80 to 100% of spacecraft and aircraft will be 3D printed. When we talk about qualification, as long as things are terrestrial based, that's fairly easy to do, because as good engineers, we're all going to go in there and test the hell out of something to prove that that strut is as good as the forged one that's on the aircraft right now. The question to the panel really is, now when I get into orbit, when I get into space, when I get onto the moon, when I get onto Mars, how do I deal with qualifying the capability of the parts when the optimal part is one that is something that can't even withstand its own weight if I were to build it on Earth? So something that's very thin is perfect for, say, the moon or in space, but I need to be able to prove that that system, that part is functional and will withstand the environments of space. So I'm forced to qualify not in a terrestrial base, and I'm curious how you guys suggest how to solve that problem.
Do you want to try that, Bill? I'm not sure.
I'll do a poor job of answering the question, but I'll try. So, you know, a big part of my background, I spent 10 years in our space division, and so I'm very aware of the conditions you're talking about. You know, when we talk about ubiquitous use, we always keep coming back to qualification, certification of materials and processes. But even at that level, right, there's, frankly, the whole reason we're partnered with America Makes is because we think that America Makes is going to help all of us kind of do some of that development. But they're not going to get into developing, you know, cryogenic properties of, you know, ULTEM 9085 because 99% of the world doesn't care about that. But we do. We care about those kinds of applications. And they're not going to care about the outgassing properties of these polymers because it doesn't come into effect, but it does in zero G, and we care about that. Yeah. You know, I think we're going to try to take advantage of as much as we can that's happening in sort of the industrial commons through America Makes, through some of these partnerships with universities. But fundamentally, some of these are going to, and again, it's not a real answer to your question, but I think some of these very niche specific, I'll call, applications for additive manufacturing are just going to have to be dealt with by the folks that are, you know, facing the problem. And I sympathize with the example you give. I don't know if anybody else has any other thoughts.
You know, I can say on the America Makes side of it, what I would think would be a good value for our membership would be to do mechanical material properties, for instance, but sort of an 80 percentile. You know, the rest would be done by the actual company who would use and apply it. So we can do, you know, in fact, there's an initiative started by Northrop, conversations been had with Lockheed across the board and Boeing. How about, you know, let's pull together what would be that norm? What would you do no matter what? And that might be the 80%. And then the rest of it would be done individually. So you're taking a lot of the heavy lifting, financial heavy lifting and time out of it by doing 80%. If America Makes can do that and provide that database and have it available, you know, that's one way to get this technology more pervasive and a lot easier to enter instead of having to find, you know, your internal monies to try to fund those kinds of things for every material and every process, which is crazy expensive.
And I'll just add one thing. So one aspect of your question is that you need to qualify it in the location it's made, which could be in space or in zero gravity, which is kind of a mind-blowing proposition, right? I mean, we're not just talking about qualifying stuff here like normal, but you have to do it where it's going to be built. And that just, I don't even know what to say. That just makes
well, they did it with whatever they used to get up there initially, they've done it. And I guess it's, you know, I look at it and say, well, you know, if you're looking at the microstructure of the materials of the rut versus this, you know, you got to mimic that because you know this works.
Right. So you can
Make
extrapolate.
it like that.
Right.
You know, that's the first step. And then, of course, once you get there will still be the requirements to say, well, that's okay, but we need to do more. And that's where, you know, you have to find a way to do that.
Right. And the second thing I would say is that maybe a lot of the additive manufacturing processes today don't have enough process control, that they're sort of open process.
That's not a maybe. That's a very positive. That's a true. That's
Okay.
a true.
So the process control could help in that regard.
Yeah, a lot of work to be done there.
Right, right.
So, great, thank you.
Yeah.
Anyone else on that one? So I'm going to go to the next question, and I'm going to send this your way, Bill. One of the barriers to expanded use of additive manufacturing in industry is training and equipping the engineering community to exploit its unique capabilities. Are the engineering, design, and analysis software tools keeping up with your needs, the industry needs?
Well, I'll echo some of Dan's comments. I think the short answer is no. If you look at, and I won't pick on any particular tool, but you know, I think any of us in the industry have used all the major CAD suppliers and analysis tools. You know, if you look at those tools, they're building on 20 plus years of evolution that was rooted in feature-based design, parametrically driven design. And at the root of that, you start off a design by fully characterizing and defining every aspect of what you're trying to manufacture, every dimension, every tolerance, and then you control that throughout the entire life cycle. With additive, and that lends itself very well to conventional processes in the past because that's how we machine parts. So the tools sort of mirror the manufacturing processes. So when you're a designer, you're building parts, you're starting with primitives and features like chamfers and fillets and rounds and extrusions, which all make sense if you're doing conventional manufacturing. But when you talk about additive manufacturing, again, most of those things don't apply anymore. You know, you're not bound by that, and you know, what we need are tools that have pre-built features like varying density structures and lattice microstructures, and have sort of integration between the design tools and the analysis tools that know what to do with that. You know, we know that the capabilities exist. We're doing it in production. We're experimenting. We've got research on how to make things. You know, a big interest in biomimicry, for example, right? You know, what does nature do? You know, how do we model our structures with what has been done much more eloquently than we can do? But our designers don't have any way to do that. You know, I was talking to somebody before the panel up front here. Topology optimization. I mean, that's something we've been talking about for a very long time. That it doesn't even come into the conversation with, you know, the typical design tools. But with additive manufacturing, you literally can put material anywhere you need to. We have the tools that can tell us where the material needs to be. We have the machines that can put it where it needs to be, but we don't have the design and analysis tools to help us design for that. So I think they're lacking today. I know we are, part of our process at Lockheed Martin, we work pretty closely with all of our major CAD and CAE and CAM suppliers to try to identify what our needs are and try to push the suppliers to address, you know, our needs, and we think our needs are representative of the industry as they look at mods and updates and tech refresh on the tools. But this is a big area, and I think even the idea of parameter and feature-driven design, which is where I think we've all in the industry grown up through, you look at direct modeling tools now that, you know, are 180 to that paradigm. I think you're going to start seeing a lot of direct modeling tools have a niche market with using additive manufacturing because I think there's a better impedance match between those types of things than feature or parametric driven tools.
Eric, do you have any, coming from academia, do you have any thoughts on this in terms of design tools and seeing how, you know, the universities can play a role in moving?
Well, I do have a lot to say about it. Oh, first off, as an electrical engineer, you know, you guys say terms like, well, struts and things like that, I'm I don't understand that. But I can tell you that we're trying to put electronics into structures, and so I want to put two chips together, and then I want to route them like a printed circuit board. And there's no software that does printed circuit boards and structures together. So that world is completely not
That's all open.
Yeah, it's all wide open.
I mean, this whole field is just opening up.
It's just completely
a plethora
open.
of other places to go.
Yeah, it goes back to the question of the doctoral student from Georgia Tech. It's like the systems engineering approach. It's not just electrical engineering and mechanical engineering. It's the microfluidics, the propulsion, the combustion, the thermal
Materials.
Yeah, the materials. Everything needs to be added.
That airplane that we printed and flew was that its control surfaces were memory-shaped material.
Right. Oh,
It was like, okay, this is cool.
So
Let's do it.
is that a part of your CAD package? Probably not. Yeah.
Probably not, but you can do it.
Right.
So, well, yeah.
To mirror what he was saying about the structures and the lack of software, I mentioned earlier about tooling for production and making it lightweight and putting the structure where it needs to be. That's only one aspect of the thing we're dealing with too, right? If you get into injection molding and some other types of manufacturing processes, thermal management of the tools is very important. So conformal cooling and being able to put the material where you want it and not where you want it, to be able to flow some type of liquid or gas through the tool, it would be huge to companies like Ford, where we're making 1 million of these things a year. It makes a big difference if I can put one out every 30 seconds or if I can put one out every 15 seconds because I'm able to manage the tool. So exactly right. There's a lot of software and design tools that need to be created to help with those type of applications.
So, as prior to joining 3D Systems and being a small business guy, and you look at these OEMs and you say, where's your head at, and why aren't you thinking about this stuff, and why aren't you leading the way? So I still can't answer that question, but what I can tell you is that they are paying attention to these problems, and we talk about what this whole hype, if you will, has done. It's made the OEMs pay attention to some of the things that we've been worrying about. The guys who are making parts, the guys who want to see this technology become pervasive and then part of our manufacturing toolbox. To that, I know that there is people talking about putting add-ons into CATIA or NX or Pro-E or SolidWorks that allow you to be able to pick the technology, pick a material, perhaps apply like a lattice structure tool or topology optimization, and in my case, I actually worked with Georgia Tech since 2007 working on a software to develop a conformal lattice structure. And our vision, the professor down there, Dave Rosen, and I, was always to put this into the CAD system. Give it to the design engineer, the aerospace guy, because he's not going to let us touch, or she's not going to let us touch their parts. We want them to use the technology, but the technology, if they do it, it would have to be used, realized through a manufacturing like additive, a manufacturing process like additive manufacturing. So, that's where I think we're going to become far more, it's going to become far more pervasive within the manufacturing community if we put the tools where they belong, and that's what the people do in the design, and they can select from a menu what the right process is, whether it be FDM or selective laser sintering, and the host of opportunity is huge for those CAD system manufacturers, OEMs, to get on the stick and do something. But I think there'll be a lot of groundswell with plugins to make that happen. I know it's happening. So I think that's one way we can get around that problem. So there's a business opportunity, I can tell you that. Any questions from the audience on that? We have about 12 minutes left here, so if not, I'm going to move into this question. I'm going to direct it to Eric. So in the current global economy, the ability to embrace and lead in the use of new transformative technology, such as additive manufacturing, separates the leaders from the followers. Okay, let me read the whole sentence again. In the current global economy, the ability to embrace and lead in the use of new transformative technology, such as additive manufacturing, what separates the leaders from the followers? What was left out of the sentence? And then it continues with how is the U.S. doing and what needs to be done to ensure that we are a global leader in additive manufacturing.
Well, I would start by saying historically, I think 3D Systems, Stratasys, the U.S. was very much in the forefront inventing this in the 80s. I know stereolithography might have had some Japanese patents, but a lot of this technology was invented at UT Austin and 3D Systems. Now, I know the UK is definitely investing a lot. The University of Nottingham, they're doing a lot. Germany has a lot of companies that are coming on. And Asia obviously is investing a lot in this. So, okay, so the question is, how is the US doing? So I think we started off strong, and I think we're in jeopardy of potentially losing our place in the world in this area, given the interest of the rest of the world, for sure. And that we need to have a very concentrated effort. And I think NAMI, or America Makes, is a small first step. It needs to be much greater than that. I personally think that it needs to be something on the order of, Kennedy's, rice speech about Texas playing rice and going to the moon. We need to invest billions, not 30 million.
Right.
I think it needs to be a huge investment.
America Makes agrees with that, by the way. Right. Well,
that's my view.
I think to that point is that some statistics. Terry Wallers, who is an industry consultant, has been in the industry for 20-some years. He had gone to China last year and picked up some good data points, and one of them was in the slide. I meant to point it out in terms of the industry growth. But what is really relevant to this conversation is that the government invested $30 million, and it's not all they've invested, but that's what is publicized. But but it still pales on what the Chinese are doing.
Right.
One province, $300 million. One province in China, $300 million. They're saying they're going to invest $2 billion. UK has invested significantly more money than the US, and so has Europe. All of our metals technologies, except for Siaki and the lens process, but the ones that have been adopted, the powder bed fusion technologies, have come out of Europe, which is, not a good thing. And I think it's changing, but, it's things like that have to change and get investment back here. But the growth areas where we've seen a lot of the innovation has been in Europe. And I think unless we do more, we're going to see a lot of it coming out of China, and it's going to take us to lunch if we don't do something about it.
Right.
From the utilization standpoint, I was involved with a panel at Clean Edge, recently, where they talked about the utilization, not necessarily the development. And at that data point, about 6 months ago, the United States was about 50% utilization of additive manufacturing. Europe was a close second, I think right around 30%. And Asia was actually fairly small at the time, but that's going to change very quickly. The manufacturers like Ford and Lockheed, some of the other companies, are really embracing the technologies, but I think the rest of the world's going to come right along strong and maybe take us over if we're not, really pushing the edge.
Any thoughts from the audience on this subject? Okay. Any other comments on this? So I'm actually going to circle back to the question that I left off, because I think it does have some relevance as maybe a good way to wrap things up here. What Ed wrote here was regarding our panel topic, additive manufacturing, a transformative technology. Just how transformative is additive manufacturing or 3D printing? I think it's a good way to kind of like bring it all home and look at this in terms of your thoughts and how you see this within your organizations and outside more big picture perspective. I'll start with you, Dan.
Me?
Yeah.
I think my slide with the Star Trek replicator says it all.
Yeah. Okay.
Next.
Okay.
I talked a little bit about it, but from a transformative perspective, again, some of those examples I gave with the propellant tank and the F-35 primary structure, if you look at those, they look exactly and they function exactly like they did manufactured conventionally. We're not even scratching the surface of what's possible in terms of utilizing additive manufacturing, design for additive manufacturing. We look at, Ed Morris talks about additive manufacturing, not only teaching people about additive manufacturing, but using additive manufacturing to teach. we're finding that we're getting a lot of interest in additive manufacturing from people within Lockheed Martin and from universities and students we're trying to recruit that we typically wouldn't expect. You would expect it from the mechanical guys, the materials folks, maybe some of the manufacturing folks, but we've got software engineers, systems engineers. These are folks that kind of are part of that maker community that before additive manufacturing didn't really feel like they had a way to connect with something like that. They kind of picked a path that wasn't hardware related, and additive is opening it up to almost everybody. And we're seeing that not only change how we design things or how we manufacture things, but also the kinds of people we look to populate our design teams, because they all of a sudden they have a voice that they didn't have before.
So one of the things that I've heard stories about, and I can see it as someone who manufactured parts for engineers and designers for a lot of my for 20 years. That role is going from my shop or shops like ours to the desktop of the engineer and designer because of the cost of the printer. They can now do the fail forward fast right at their desk. And that's transformation. I mean, so then you'll begin to start seeing more integration of that thinking, that thought process, because they'll also begin to try, the what ifs. What if I made it this way? Well, I can manufacture it because I'm here. If I get printed, I can manufacture it. So, whether it's true or false. I see we have someone standing ready to queue up for a question, please.
Yes, my name is Joseph Honick. I'm a fifth-year undergrad aerospace student at University of Cincinnati. And as a member of the maker community, I guess you could say, I have a 3D printer and a 3D scanner on my desk at home.
Cool.
And I have successfully made dies and parts at Barnes Aerospace where I work from my desk. And I'm just wondering if this maybe is a threat to the bigger companies where someone like myself can fully design and develop the manufacturing process or system from my desk and in my room. And the only thing keeping me from possibly opening a small manufacturing, maybe it'd just be brackets or sheet metal for now, but essentially from my room.
Well,
whether that will saturate the market with designers and
I think
anyone
that's
to make anything.
I think that's what's actually transformative, is the fact that it's pushing this. It's opening up the technology, the ability to make parts again, where someone couldn't make parts. I have an experience that I had. I was in one of these labs in Philadelphia. One of these fab shops where they kind of sort of came out of the whole makers movement, if you will, and not knowing what I was going to see when I got down there, it was an open house. The place was jammed out into the street, and it was in February. I'm like, this is crazy. What did I come down here for? And I'm waiting in the street to go into to a shop. And so I went in, and they have all the, lots of different equipment, ways to make stuff. And it was in the university area, so it was the right community, if you will. And I bumped into one of my engineers. I said, Todd, what the heck are you doing here? He says, I come in here. He says, I have a membership here. I says, well, you have a whole shop. He says, well, I live down here. And I can come in here, and I can, for a fee, I can come in here and I can make stuff. I says, wow, that's just crazy. So I get it. I think it's really giving a tool to people who want to make stuff, want to create. And I think that's a wonderful thing. There's nothing, let's embrace that. So let's embrace it for the kids in school. Let's embrace it for K through 12 and push it back even further to re-engage that mind to get them into the engineering world and into making things again. I think that's really what we need to have in our, start to build that back into our society. That's what's really been pushed away because manufacturing had this, it was tainted. Who wants to be a manufacturer? So.
To build on that same point, as you mentioned, I teach at Tech Shop Detroit 3D printing and 3D scanning. And I see several of the Ford engineers in there doing work for themselves and for others, right? And then in the engineering community within Ford, several of the engineers have actually developed their part for the vehicle at home, in their office and in the house, scanning, printing. And they come in and they say, okay, I've made this part on my MakerBot, it's not a functional part, but then they come to my lab, say, okay, can you make me an intake manifold or whatever that I can bolt on the engine and run 100,000 miles and continue my development. So I think it's a great extension of where we're at today. As far as the impact on, is it going to affect the company? I don't really think that Ford Motor Company at least is going to go outside to somebody else to get a design, but we encourage our people to go out and do the work at home if they want to and tinker. One of the things I like to say too is I'd rather have an engineer that didn't do as well in school but knows how to tear his engine down at home and put it back together and get it running than to have an engineer that gets a 4-point but doesn't know where the dipstick is.
I can't change my oil, by the way. But yeah, in the age of Napster, it's an interesting question, right? You can replicate something and start building it, and I mean, maybe you're too young to know Napster, but yeah, I mean, it's a fascinating issue, the idea of intellectual property and the ability to reverse engineer something and start building it. It's a problem that we haven't really covered yet.
Yeah.
I think unless you can become an approved supplier to a highly regulated industry, carry on and see if you can make some money.
Well, right now, actually,
You might need your own testing house as well to complement your printer and your scanner.
could be a plan.
Yeah, I think someone mentioned it earlier. It's a great education tool. I mean, first robotics, STEM. I mean, American Makes has a initiative to, along with industry partners, 3D, Stratasys, MakerBot, to really make this pervasive in the education community, so that they can make things as they think of create things and make them. So it's all good. There's all good. A lot of goodness in all of this.
From a supply chain side,
Thank you.
We've got over 40,000 suppliers in our supply chain right now, but there's historically been a barrier to becoming a supplier, one that you need a lot of capital equipment. Again, additive manufacturing allows you to become a manufacturer. Now, the question of whether or not you'll get qualified in a very tightly constrained, tightly regulated industry, again, more power to you. If you can make it cheaper and at the right quality, I think from a supply chain, we like that. The idea of IP is a little bit different. It's the negative or the other side of the sword. But from a supply chain side, go for it.
The whole idea of with e-commerce and having localized manufacturing is very much made possible, using additive manufacturing in some of these inexpensive printers that you can buy for your home now. I mean, so it's a whole community of industry that's beginning. Whether you subscribe to the stuff that you're making or not isn't not the issue. I mean, I personally don't, but there are people who do, and I think that's part of a community that's developing, and it's jobs. It's creating jobs. It's putting people to work how to make stuff and making stuff. It's all good.
Kind of tying this in with the last question we had, I mentioned that we have engineers working at Tech Shop making stuff and then coming in for a later part. Part of that is because we have 5 major labs in Ford Motor Company. I make 20,000 parts a year. I don't have enough capacity in Ford to make all the parts that we need to make, right? I could have 10 labs my size and we still wouldn't have enough. The use and the education and the knowledge is really pushing what we can do. So having folks go on the outside and get started and then come back in to use our technologies really helps.
There's something scary about having a Bridgeport and a lathe and a bandsaw in your house in Manhattan, but you can buy a printer and do the same thing almost. I mean, it's not the same material, it's not as precise, but usually those people who have them in their shops aren't looking for precision, or looking to create something three-dimensionally so they can try it. And I think that's all cool stuff. I mean, I sail and I have a watch that I love, and the blasted thing's all molded watch, all molded band, and it lost that thing that keeps the tucked in. So I had somebody print it for me, and I had 5 of them on my desk. I'll have it for 25 more years.
There you go.
It's simple stuff like that that just kind of makes sense in the beginning. I think we're wrapped. Thank you.